Hi and welcome to this introductory lecture to simple linear regression using R. In this short lecture, we go through the simple linear regression itself, the mathematical model of SLR, the implementation in R, and interpreting the results that we get in R. A simple linear regression model is actually a relationship between two quantitative variables, a dependent variable y and an independent variable x. We put our independent variable on x-axis and our dependent variable on y-axis. Our objective is to find the linear equation that best predicts y out of x. That means if we have x, we can use this linear equation to predict the values of y. The mathematical model behind the SLR is as follows. Y, which is our left-hand side variable, is beta 0 plus beta 1x plus epsilon, where y is our dependent variable, x is our independent variable. Beta 0 is the intercept when x is 0, and beta 1 is the slope or the coefficient of x. Epsilon is the random error term or the disturbance. For interpretation, obviously both beta 0 and beta 1 are important, especially beta 1, which gives us the amount of change in y as we change x. In R, we use our dataset tips and we try to run the linear model of y over x. In this case, y would be our tip and x would be our total bill, and we try to see if we can predict tip out of total bill. We do expect that the higher is the total bill, the more tip will be paid, but that's something which we will be testing. We then use summary model 0 to print out the results. For interpretation, of course, we need to check beta 0 and beta 1. Beta 0 is the value of y when x is 0. In some applications, this does not have a real-world implication. For example, in our case of total bill of 0 doesn't make any sense because anybody who is coming to the restaurant, they buy something, therefore they pay something. But in some other examples, letting x to be 0 makes sense. In those cases, beta 0 is the value of y when x is 0. Beta 1 though is a more central coefficient that we need to look at, is giving us the change in y, in fact the average change in y as we change x. And r squared is the proportion of variance in y explained by x. Remember that x and y are correlated. There is a correlation existing between x and y, and r squared giving us the percentage of variation in y that's being explained by x. Obviously, the question would be, how about the rest of variance in y? The rest of variance in y is explained by other factors which are not part of our simple linear regression model. The p-value gives us the significance of beta 0 and beta 1. The smaller is the p-value, the more significant is the coefficient beta 0 or beta 1. Next, let's implement this example in R. As always, we upload our dataset dt read.csv tips dataset, the names of the variables that we have. Especially our focus is on total bill and tip variable. We want to use our tip variable as dependent variable and our total bill as independent variable. First of all, we have to check the correlation. How much is the correlation? Is the correlation high enough? It's about 68%. So 68% is a moderate leaning towards high correlation. You can check the linear relationship between total bill and tip by plotting the scatter plot. As you can see here, especially below $30 total bill, the relationship between total bill and tip is more linear. Obviously, as we are moving towards higher or larger total bills, the relationship is getting more scattered and it's less linear because there are a lot of variations and lots of ups and downs here. But the good news is that we are not having a lot of observations in that part of the graph. We are having more observations for the total bill below 30. In order to run the model, we just call it model 0. The function for the linear model is lm, taken from the linear model, our y variable, which is tip, then our x variable, which is total bill, and then we run it, and then we summarize using the summary function this model, and that gives us everything that we need. For example, the estimated value for beta 0 is $0.92. As mentioned earlier, the interpretation of this value in our case, this doesn't make sense because when x is 0, total bill is 0, that's not possible in our case. However, the estimated value for beta 1, which is 0.11, is a more significant value for us. And it says that on average, the tip will increase by 10 cents by every additional extra dollar in total bill. And as you can see here, this is very significant because the p-value is nearly 0. When we have 3 stars here, that's the sign of highly significant impact of x on y, in this case total bill on tip. So we can say with high confidence that in fact with every additional dollar in total bill, on average, the tip would increase by 11 cents. And R square here is 0.45 or nearly 46%. That means 46% of variation in tip is being explained by total bill. The other 54% variation in tip, it's explained by other factors. Could be gender, could be day, could be anything else. Thanks for watching and good learning.